Today we have Bashi Mandava, who is a fifth-year PhD student in the Lean-Weber Institute for Theoretical Physics, working on dark matter direct detection. Outside of physics, she enjoys cooking, baking, badminton, and whatever outdoor adventures that her friends drag her into. We are very fortunate to have her here today, so please take it away.
Thank you for having me. This is my first time being at an astronaut talk. So I'm really glad to know that this exists. And I've been told that this will be to a mostly general audience. So I've tried to make the talk without too many details and more accessible as well. But if I'm skipping some topics and if there's slides that go over your head, please feel free to ask lots of questions, and I can answer your questions and clarify some things. So yeah, as I've been introduced, I'm a fifth-year PhD student in what used to be called the BCTP, now it's LITP, and I work primarily in dark matter direct detection. I won't be going into too much of my own research, but I'll be giving a broad overview of what we know about dark matter and what evidence we have for it, and sort of how we look for it in astrophysical objects and in a lab space. Okay, to start with, I'll start with sort of a big timeline of the universe. You may have heard of this. People like to say that we started in a Big Bang, and then there was this rapid expansion of space, the so-called inflation that occurred very quickly. And then, atoms and stars and galaxies started to form. And after many billion years, almost 14 billion years, we come to present day where we have lots of, galaxies, clusters, and also human life. So before delving into too much, I'll start with some basic facts we know about our universe. We know that it is very smooth and uniform on large scales. And I will show you the cosmic microwave background in a bit, which sort of establishes this. And we know that it is expanding and that expansion is accelerating. That is a bit more of a recent result. And then we also know that it is mostly made up of matter that we don't see. And this last point is what I will focus on. So what evidence do we have for dark matter? First piece of evidence we have is rotation curves. This is a picture from, I think, 1970s by Vera Rubin's team, who sort of, were looking at many stars in a galaxy and were trying to map out how fast they're moving as a function of how far they are from the center. So from Newton's laws, what we expect is that as you move farther away from some really big, massive object, you tend to, your velocity should drop with radius. So you tend to go slower. If you want to stay in circular orbits, the farther you are from it, the slower you're moving, the closer you are, the faster you're moving. And so if you sort of, make a calculation based on how much mass you have in say, a galaxy, you know that there is this, very high concentration of stars, roughly at the center. We call this the stellar bulge. And you have a more, broader distribution of stars that we call the stellar disk that is also very massive. And then finally, we have some sort of a gas disk, which is a more, distribution of disk gases in your galaxy. This roughly makes up what we consider to be the visible matter available to us. So, if we make a plot of what is the rotational velocity of objects moving around here versus here versus here versus here, we would expect it to look something like this. Most importantly, it should fall as you go farther away. And so in physics terms, this would be velocity going as 1 over square root over r, so that the curve should really fall with radius. But what we instead see is that it is not falling, it is almost roughly flat. So this is not what they were expecting to see. They were sort of trying to just map out the distribution of stars, and instead they found something that was really puzzling. And to this day, people have done even more extensive observations and measurements of not just stars in a galaxy, but galaxy clusters, etc. And we still see this. This result still holds to this day. And the most likely explanation that I think is that there is some really huge halo of missing mass that we don't see, that is not visible, that we haven't accounted for. And if you account for it, it just pulls it up because now you have a whole ton of mass that is just covering your entire stellar distribution. So this was, one of the earliest sort of piece of evidence that we had for dark matter. And I'll give you a couple more examples that I think are more well established as we come towards like precision cosmology and sort of more detailed measurements and just more advanced technology. So the second thing is called the bullet cluster. But before going into what the bullet cluster is, I want to give you a small sort of like background into gravitational lensing. What we know from general relativity is that light bends under gravity. What this means is that if you have a really massive object and some light is passing around it, that massive object can actually bend the light that is passing through it. You can think of this, the analogy that we like to use usually is like a blanket, and you have a huge blanket that you're just holding with your friends, and you're holding each corner of it, and you throw a ball into it. And the blanket will sort of, move around, shift around, and it will just follow the mass that you put in it. If you move the ball, the blanket is going to sort of change its shape based on where the ball is. It's not a perfect analogy, but I think it helps us sort of visualize what it means for light to bend under gravity. So why does this matter? It matters to us as observers on, Earth, because when we're looking at really far distant objects, for example, here I have a quasar, and this is us, where, you can just think of a quasar as like a really big star, etc. But what's important is what's happening between this, far away object and us. In between, you have a ton of galaxies, and you can have really massive objects. You can have just one galaxy that's just really big, or just a distribution of them that collectively make up a big mass. But as long as you have some massive object in between, it is going to bend the light rays coming from this faraway object. So all of these are going to look to us as different points in space. So there's like 3 or 4 here. And what that means is, I think it's easy to see in this little animation if it works. So you sort of see, if we start here, and this is, and this is some faraway object, and the light is traveling, and then it gets bent, and this is us. What we end up seeing is what we like to term as sort of like multiple images of the distant object, or even distorted images like this, which is, sort of not natural, but it's a hint that light has been bent by some, intermediate mass that we're seeing. What does this mean for the bullet cluster? So for some background, the bullet cluster was, 2 clusters of galaxies. You see the smaller one here on the right, and you see the larger one here on the left. And they both collided some time ago, and we can look back and see, how this collision happened and try to figure out, what we can learn from it. And the pink stuff is stars. The pink stuff is basically, stars with a lot of friction, so that when they collide, they'd like to just come together. they tend to just clump. And then the blue stuff here is gas. Gas can be really massive, and for this cluster especially, the gas makes up most of the mass. But this gas, it doesn't have a lot of friction. So when two objects sort of collide, the gas tends to just pass through, and that's why we expect the pink stuff to be in the center, whereas the blue stuff is more, distributed on the outer edges. So what we would expect from, gravitational lensing is if you lens such an object, you can map out where most of the mass is concentrated. And what we expect is most of the mass should be centered on the gas, because I just told you that the gas is the most massive stuff in this galaxy or in this cluster. What we actually find, so these are contours of the mass distribution. And what we find is that the centers of the mass are slightly actually deviated from the blue stuff. You see it a bit more obviously here, but it's not centered on the blue stuff. It's actually, farther away from the blue stuff. And this is one of the other, damning pieces of evidence for dark matter, because not only do you see that most of the mass is concentrated at a position where we don't see stuff. We don't see, majority of the gas there. We don't see majority of the stars there. And that's what makes up most of the visible matter to us. So it's actually, farther away, which also tells us that dark matter behaved a lot like a gas. It also was a very, yes.
How do you determine the distribution of mass through gravitational lensing?
So there you can go into a bit more details, I think. On top of gravitational lensing, you can also use, other probes, but you can also use like weak lensing, strong lensing, etc. to figure out more details there. But I think for this case, you also use like a combination of astrophysical probes. But gravitational lensing is sort of the main thing that you use.
What do you mean by astrophysical probes?
So not just gravitational lensing, but like X-rays that we observe from astrophysical probes, and that's in the sense that this is an astrophysical object.
Okay, so satellites in orbit around the Earth using X-ray detectors.
Yeah, so I'll talk about like the Fermi telescope, which looks for gamma rays, especially. And you have like a whole slew of them at different spectrums of light. Right, so, what we're finding here is most of your mass is concentrated at a point that does not coincide with the centers of the visible mass. And then the final piece of evidence is the cosmic microwave background. This is a fairly, I think, detailed piece of evidence, and it is hard for me to wrap around my head as well. Trying to explain this is relatively hard. So, if there are details that I'm missing or if it doesn't make sense, feel free to ask questions, and I'll see if I can clarify. But to build up to the CMB, I'll provide some background. And, I told you earlier that in the beginning, there was just this, soup, or what we like to call like a hot dense plasma of photons and quarks and baryons and all sorts of stuff. And then inflation occurred for like 10 to the negative, there was some quantum gravity phase, inflation occurred, and then you have the soup. And I will, focus on the soup for a bit because it's pretty important. So initially you have a lot of stuff in there. You just have really hot, dense plasma containing photons and baryons, or I should say quarks, which I'll talk about a little later, and gluons and things like that. But as the universe expanded and temperatures cooled, you get access to nuclear fusion. What does that mean? It means that in this graphic, you can think of these guys as protons, and you can think of the blue ones as neutrons. So when you have a bunch of neutrons and protons, they can come together to form what we like to call deuterium. And once you form deuterium, thing of deuterium and the thing of deuterium can come together to form even higher, heavier isotopes. You can also have helium-3, etc. But this is a particularly important sort of event in cosmic history. And it can produce a lot of energy as well that you see in yellow and photons, of course. And this is occurring around like 100 seconds after the Big Bang. So just to put the timeline in our mind, everything is happening extremely fast. Inflation is 10 to the negative 32 seconds after Big Bang, and Big Bang nucleosynthesis is, the official term for this is still like 1 second after the Big Bang. This is going to be extended over, 100 seconds. It is not an immediate, event. It actually takes place over some distribution of time, and the temperatures are around an MeV, which I will come back to. So why is this important? It's important because now you have a bunch of neutrons and protons together forming deuterium. But more importantly, before in this soup, the photons were continually scattering off of the electrons. Because whenever you have a ton of electrons in a bath and you put a bunch of photons, they're just going to scatter off. We call this like Thomson scattering. And because there's just a whole bunch of charges here, these photons are going to find it really hard to come out of the spots to escape. But once you have neutrons and protons forming, deuterium, for example, they want to catch an electron and form a neutral atom. So that's what they're going to do. They're just going to grab electrons that are just floating around here and start forming neutral atoms, which means that the electrons are not occupied. So the photons are not going to scatter as much off of these electrons, which means that these guys are free now, free to travel long distances, and sort of escape. And we like to call this the surface of last scattering, because that event in time, prior to that event in time, all of those photons were just clumped up with all the other stuff that's in this plasma. But the minute that you form neutral atoms, they can finally start traveling long distances. So now you actually have access to photons, and photons are primarily how we observe the universe. Without photons, we cannot make any observations. We cannot look back. We cannot try to, deduce anything about the universe without light reaching us. And, this is called the surface of last scattering, when the universe finally becomes transparent to us. And that's what gives us the cosmic microwave background. So this is a really beautiful fundamental result, I think, that sort of maps out how the universe was at recombination and what sort of temperature fluctuations were at that time. So the easy way to think about this is, I think, you can put a giant antenna in the sky and you can sort of turn it around and you can measure the voltage in each direction. And that's like an angular scale in the sky. So as you turn it around, you're looking at a different angular point in the sky, and that's kind of essentially what the CMB is. And what we're looking at here is, you take this 2D temperature function and you can do some fancy math to it, and then you end up with what we call an angular power spectrum that shows how much your temperature is fluctuating at each angular scale. It has a lot of, really beautiful and damning implications for us. And each of these peaks tell us something really crucial about the universe. For example, this first peak tells us about the total matter density in the universe. The second peak tells us how much baryonic matter there is in the universe, which I'll come back to in a bit, what baryons are. But roughly you can think about it as how much normal matter there is in the universe. And then finally, the third peak is sensitive to the dark matter density. And the relative height of these two peaks is what tells us that you must have some dark matter density to account for it. If there were no dark matter, for example, this peak would be much smaller than this. And there's a lot of really cool science that goes into this. And if you have questions, I can talk about this more after the talk. But yeah, the CMB is really beautiful, and I'm really glad that it provides us with one of the strongest pieces of evidence for dark matter. So with that, hopefully you're more or less convinced that dark matter exists. And the question is, how do we look for it? We can map out certain properties that we think it should have. We know it's massive, it interacts through gravity. It does not interact with light, with a little asterisk here, because we would like to think it has some coupling or, some way of still interacting with light. What I mean by that is if it absolutely only interacts with gravity, there is no hope for us to observe it. We need it to interact with the standard model or, electromagnetism, etc., in some really small way for us to have any hope of actually detecting it in a lab or through some astrophysics, right? So, when we say dark and when we say does not interact with light, we really mean that it does not significantly interact with light. It could be that it actually does not interact with light at all, but then we're kind of screwed. And, that's an extreme that I try not to think about. And then finally, it has to be stable. So we know that dark matter exists today. We have a measurement for, how much dark matter there is. We call this the dark matter abundance. And because it has to exist today, it means that it could not have been decaying to something else over cosmological timescales. It has to be relatively stable to survive to this day. Okay, so I've been talking a lot about dark matter, but before going into how we look for it, I think it's important to sort of give you a broad overview of normal matter, matter that we're used to observing, and matter that interacts with light and everything around us. And in particle physics, we have this big model called the Standard Model that is meant to describe everything in the universe. So atoms, galaxies, stars, everything boils down to certain fundamental particles, and those are these guys. So you have the quarks. These guys make up, for example, protons and neutrons. And then you have electrons that you might be familiar with, and you have neutrinos that are really very, very light. You'll see that there's just an upper bound here. We don't know their mass. We just know that they cannot be more massive than something. But because they're so light, it's really hard to, learn things about them. And then you have the force carriers. You'll notice this, the photon, and you have the Higgs, which, gives mass to everything else, and the hypothetical graviton. We know dark matter is not any of these. We don't know what it is. We have a lot of theories for what it could be. And those theories, because we know there has to be a mass, span over a really broad mass range. And that's this. For comparison, an EV is like 10 to the negative 33 grams. But even without that, that's about, 40 orders of magnitude or something crazy like that. All to say that we really don't have a handle on what its mass is. We don't know much about it. And the best we can do is assume, break this problem up into smaller chunks and say, okay, what if the mass is somewhere here? How would it behave? What if the mass is somewhere here? How would it behave? What if the mass is somewhere here? How would it behave? And depending on what assumptions you're making for this mass, you will look for it differently in a lab. I like this comic by, I think, PhD Comics, that gives you sort of a picture of dark matter candidates in comparison to everyday objects like space cows, apparently. But but for comparison, the bees are somewhere around here. And pollen is somewhere around here, and then you have, some very well-established candidates in our field, like axions and sterile neutrinos that I'll talk about soon, somewhere around there. So very, very small. But you can also have, really big objects like black holes. You can have primordial black holes, which, if they turn out to be dark matter, will also be really troubling for my field specifically, because we look for it on Earth, and there's no black hole on Earth, so it makes things tricky. So there's a lot of assumptions that we make about this to sort of try to figure out what it could be. So before going into a bit more detail on the mass range, I want to introduce quantum mechanics in a couple slides. So light is really interesting. I think light is, very special. And it has this property that we like to term the wave-particle duality, because it can either behave as a particle or a wave. And it started out with a couple fundamental results, and you might know that people who worked on them, got Nobel Prizes for working on them, like Einstein, for example. And the first result that I want to talk about here is the so-called double slit experiment. And what you do here is extremely simple. You just have you just shoot some light, and you have a slit, you have some wall, and it has one opening. And then you have another layer, you have a second wall, and it has two openings. And what you want to do is you just want to shoot some light through this, and you want to sort of wait and see what happens. If you think it's a particle, then you should just have a dot, right? And that's what people thought for a bit. Oh, everything is a particle. Why would it be a wave? How can you have like a spatial distribution? And what happens is you get this sequence of dark and bright spots. You have a source, you have a light source, and then you shine it through some walls. And what you end up seeing as an observer over here is that there's a bright spot, there's a bright spot, there's a dark spot in between. So you see a sequence, and we call this like a interference pattern. And what's happening is that because light is a wave, it can either interfere constructively or destructively, which means it can come together and add up, which will produce a bright spot, or it can come together and sort of cancel out, which will produce a dark spot. And then people were like, well, okay, light is a wave, that's that, well established. But people did something silly. They just did the experiment again. You can do the same thought process, but you just do it slower this time. And by slower, I mean that you sort of reduce the intensity of this light, meaning that instead of, like, say in this analogy, a bunch of waves passing through, you just have like one wave passing through. Then you would expect, okay, then there should, just be a bright spot or a dark spot, just one of them, right? And that's kind of what happens. You get, dots, either a dark spot or a bright spot. But if you wait long enough, say you set this experiment up and you let this happen, but then you kind of let this go for like maybe 24 hours. And say you're shooting only one photon per hour. So after the 1 hour mark, you will have seen just one dark or bright spot. After the 2 hour mark, you would expect to see two bright dots, or one bright, one dark, etc. But what people saw after just forgetting about this experiment and letting it sit for a while is that indeed you see a bunch of dots, but if you leave it for long enough, a pattern emerges again. You see the same interference pattern that you were seeing earlier of dark and bright spots coming in again. So it's really interesting, and I think one of the first things that I learned about that blew my mind, and quantum mechanics as a whole. But what this means is that light is both a particle and a wave. We've come to understand and sort of accept that now. But it's not just light. Massive objects and other particles also behave like this. And that's determined by what we call the wavelength, which is inversely proportional to your mass. So whenever your mass is really big, the shorter this is, and the smaller this is, and the more you behave like a particle. If you have a really small mass, you have a longer wavelength and you behave like a wave. The easiest way to think about this is, I think, just imagining a string where if you elongate it a lot, it's just more extended over a spatial region, and you have more of a wave-like behavior. If you just compress it in your hand, that's more like a particle-like behavior. And this wave-particle duality is what sort of tells us how to think about massive objects. So for dark matter also, when we're trying to build experiments to look for it, the first thing we want to think about is, does it behave like a wave or does it behave like a particle? Because the way it interacts is very different based on which one it is. And so I'll focus on a few of the particle-like candidates that we have. Some of these are really big, like black holes. Some of them are roughly in the GeV range that we call WIMPs. And then you can also have light to dark matter. If they end up being black holes, we're also out of luck. Or I am out of luck, personally, because I tend to work in the light dark matter EV to a GeV range, when they're about the size of a proton or an electron, roughly. But if they end up being black holes, which they totally can, they would just be distributed at different places in the universe, and not on Earth. And the basic strategy that we use for these guys is try to detect it in a lab. And so if they're over here, then I'm out of a job. But if they're over here, we're fine. And we have some constraints here too. We just don't know. We've tried to eliminate a lot of candidates. There's been a lot of research done, and particularly I think the last decade, to sort of narrow it down a little. But yeah, you still have a really big mass range. And one of the favorite candidates in the field are the so-called weakly interacting massive particles, or WIMPs. These guys are very, I think in particle physics terms, kind of heavy. They're about the size of a proton, and they interact via the weak force and gravity. And they became really famous because of WIMP miracle. It is not so much a miracle anymore, but the idea was that if the dark matter particle exists around the weak scale mass, then what we predict from theory, how much of it should exist today, matches very nicely with what we actually observe. So, this was what people were really hoping was dark matter. And it is also very appealing for supersymmetry, which is just where you have a theory that introduces a mirror world that has all the particles that we have. We call them super partners with different properties. But this is what a lot of people build their careers on, and we're really hoping was big, result for dark matter. And it is not ruled out yet. It is highly constrained, which means we've done a lot of experiments and we don't see it. So it tells us, it gives us a gauge for what it could not be. And so it's getting more and more constrained, but it is really, really appealing for theoretical reasons. So people still hold on to it, and we're building bigger and bigger detectors to rule it out more, but it's just as important to rule out candidates to figure out what dark matter is not before we get to what dark matter could be. And that's sort of the crux of this field as well, is sort of try to remove areas of parameter space that don't work. So you're left with something that works. The second set is light dark matter. So now you have like roughly an electron-sized dark matter particle. And both of these, again, electrons and protons are going around this, right? Or they're not going around, they're in things, but they're perfectly fine to be just moving through Earth, moving through our neighborhoods. And that's why these two candidates with those masses are fine to move through Earth. And we call this like a dark matter halo. We assume there's some density of them in our galactic neighborhood. And that's what allows us to look for it in the lab. That's an assumption, again. It's only if those guys are, in roughly this mass range that that's possible. But for the light dark matter, you have a whole slew of models. I won't go into too much detail about what these models are. I think it's more informative to talk about like how to look for it. But here, the one thing that I really like is sterile neutrinos. So I told you earlier that we have neutrinos around us, which are just normal matter, but are extremely light. And here on this is one other mystery that we don't understand, is why the neutrinos are so light. Their masses are incredibly small compared to everything else, right? That's orders of magnitudes. And we don't understand why that has to be. There are many theories, of course, and one of them is the sterile neutrinos, where not just, on top of being dark matter and solving the dark matter problem, they would also act as heavier twins of the usual neutrinos. So like this cute little animation here, where these guys would be the dark matter particle, the sterile neutrino, and these would be just the standard model particles, the normal neutrinos. And we call this a seesaw mechanism, where the masses of these two are inherently linked. One guy is massive, the other has to be very, very light in mass. And that would explain why the neutrinos in the standard model around us are so light. We like to, I think, build theories that solve more than one problem. So this can solve the dark matter problem, but it can also explain why neutrinos are so light. On the wave-like front, I'll just talk about one candidate I think is particularly appealing, but the rest behave very similarly. So if your dark matter is more of a wave, one, it's extremely, light in mass, so ultralight. And there's, again, a broad class of models here. We call them axion-like particles, and there's QCD axions. This guy, QCD axion, is particularly nice because, again, you solve two problems. You solve the dark matter problem, but you can also solve the strong CP problem. And the strong CP problem is where you, well, to go into the strong CP problem, I'll talk about H2O first. So for the water molecule, you have oxygen and you have two hydrogen, and you have sort of, two lone pairs on oxygen that are just floating around. Why does that matter? It matters because these guys are, bonded to hydrogen. These guys are also bonded to hydrogen. But the electrons here are just sitting around and they don't like each other. Electrons just repel each other, right? They have the same charge. They don't like to sit together, which means that they take up more space. So usually you might expect something to just be like this. It could just be, straight, where you have oxygen here, hydrogen, hydrogen. But because you have that lone pair up there, it pushes these guys inwards so they can have more space. And that creates, what we like to call a dipole moment. But the same thing happens with protons and neutrons, or specifically the neutron. In a neutron, I told you earlier, it's just made up of quarks, but specifically it's made up of an up quark and 2 down quarks. So for a neutron, we would also expect the behavior like this. The up quarks and the down quarks, the charges are different. And the behavior should, more or less resemble this, where you should have some angle, some theta angle between the up quark and the down quark, just as you do between the hydrogens or the oxygen and the hydrogen. It should not be flat. What we actually see is that it is actually very close to flat, even though these charges are different. And we don't know why. Still trying to understand that. And and we don't know why nature prefers that orientation over this. In the QCD axion, when you build up this theory, it is able to sort of explain this behavior in a very nice way. And we really like this candidate because it's able to explain not just the dark matter problem, but other problems as well. So I'm sort of giving you a highlight of the candidates that are able to do more than one thing. But there's a lot of dark matter candidates, that simply are just dark matter and don't have to solve some other problem that we don't understand. Nature doesn't have that preference. Nature can just be like, you're dark matter and you do nothing else. I think as theorists, we just like to just solve 2 problems at once or 4 problems at once. And these are the candidates that are very appealing in that sense. Okay, now that you have some overview of what dark matter could be and what sort of models we have in our minds for the theoretical front, I want to talk a little bit about how do we detect this experimentally. We call this the Holy Trinity, or I call it, and basically what you're looking at here is 3 different ways of detecting dark matter. So here the dark matter particle, I'm just calling it chi, and then you have some normal matter, like an electron or a proton, which I'm using this phi to represent it. And you can look for dark matter primarily 3 ways. You can, go this way to the right, which we call direct detection. And you can have some dark matter particle, hitting some normal matter, can just collide, scatter off some standard model or normal matter. And then it goes on its way and then it deposits something. So this state can change. So I'll talk a little bit more about this, but basically, if you have some atom in a detector and dark matter comes in, hits this atom and goes on its way, this atom can know about it. The dark matter could have deposited some energy or made it hotter, made a cold splash of light, etc. And that's how we would detect it. And that we broadly call direct detection. And then you also have indirect detection, where you look for annihilation products of dark matter. So you just have 2 dark matter particles coming in, colliding with each other, and producing a whole bunch of other stuff. And that other stuff can be electrons, can be pions, can be photons, and we look for that stuff. And then finally, we have collider production, where you go downwards here, so you have some normal matter coming in together, creating dark matter. So we do this in colliders. You have like the Large Hadron Collider, where you have a really big and energetic beam of protons or electrons, and they come together, collide, and theoretically can create dark matter. So these are the 3 main sort of ways we look for dark matter. So for direct detection, like I said, we hope for dark matter particle to hit some normal matter and create some energy, modify this normal matter in some significant way, go on its way. And the way you look for it depends on how massive it is. So earlier I told you, you want to sort of do what we call a kinematic matching. If you have bowling balls, right, and you have a big bowling ball, if you hit it with a feather, it's not going to do much. it's just going to stay still, and it's really hard to tell that anything has happened. But if you hit it with another bowling ball, of course, you'll see it. There'll be a big splash of energy and, noise and stuff. And that's the primary idea behind direct detection. If you have a massive dark matter particle, you want your target or detector to also be big. So for this mass dark matter, you have these really huge tanks of xenon atoms, because they're roughly around the same mass. And they're in a liquid form, and what happens is when dark matter comes in, it would create a whole splash of light when it first hits that xenon atom. And then, it might even excite an electron. It has some electrons, so it can eject some electrons. And then you apply some electric field to drift these electrons up to the top. And then we have photomultiplier tubes or some, fancy sensors at the top and bottom that can tell you where this collision occurred. Because you make a big splash specifically around this region, right? That gives you the distribution, in the X and Y directions. And then there's what we call a time delay between this first signal, or prompt scintillation light, and some delayed signal, S2. Both are light, but this one comes first, this one comes second, which means based on how long it takes for that second splash of light, you can also calculate where this occurred in the vertical direction. If this occurred here, it would have taken much longer. If it occurred here, much smaller. So, this entire setup is meant to sort of figure out, has a dark matter particle hit our detector, and where did it hit it? And the primary interaction, like I said, is with the nucleus, because you're dealing with a nucleus-sized dark matter particle. So it just comes in, hits the nucleus, goes on its way, and whatever it does within the detector, you do a lot of data analysis to sort of try to figure out what the mass was, where it occurred, and what else it did in your detector. And then you have light dark matter detection, where it's more closer to the mass of an electron. It's a little smaller. So now, of course, you interact directly with the electron. And then here you have a different setup. Here you instead have a crystal, and you cool these crystals down to really small temperatures. We call these cryogenic detectors. They're really, really cold. And the idea is to minimize thermal noise. We want to minimize any amount of heat, so that whenever dark matter particle comes in, it generates heat, and it can also excite some electron, which again we apply an electric field and drift it upwards, which will create more heat, which I'm using this yellow bands to represent. But that's your primary source of signal. In the previous one, you were using light to detect this. Now you primarily use heat, but you can also have more than one source for this. Usually all of these detectors use two. They also have light, they have heat, they have charge, etc. A combination of things to maximize your chances. But you really do need to be extremely precise, because a lot of normal matter creates heat. It's really hard not to create heat. I create heat when I'm talking, when you're walking. Just any movement can create heat. So you have to be extremely precise, and I'm really glad that I don't have to do this. It's the experimentalist's job to do this. So yeah, so hard one. And then finally we have axions. Like I said, these guys are much, much smaller, which means because of the wave-particle duality, they have to behave more as a wave. And I don't work on this, I don't know many details, but from what I understand, it's really cool. And the idea here is you have a big magnet, and you have strong magnetic fields. And these particles are slightly special because they have this ability to convert into photons. We call it the axion-photon conversion. And here the axion can come in, and it can interact with the target material, and it can actually just directly convert to a photon. And that photon is what you would, read off as your signal. And that is going to be proportional to the mass of the axion. So this is a resonant search, where you try to be on resonant with the mass of your axion. Okay, so that's for direct detection, where you do things in a lab, basically. Indirect detection is where you look for the products of dark matter annihilation. So dark matter particles can come together and then create a whole bunch of new particles, like, photons, for example. And then we look for that. So this is a recent result, or a mystery, from the Fermi telescope. Back to the question you were talking about. And this is a galactic center axis that we observed at the center of our galaxy, Milky Way. And we've been trying to understand why there is a huge red band in the center of the galaxy. We would expect more, isotropic distribution, basically. And this red band is a couple GeV higher than normal energies. So it's a whole flux of like really high energy photons, gamma rays. So people have some theories about it. So earlier I told you, dark matter can come together and create a bunch of stuff, and that stuff can be really, really energetic sometimes. So that's, high energy gamma rays or photons, and you just have stuff coming together, creating light. That's one possible explanation. The other is, and this is a personal favorite, millisecond pulsars. So pulsars are sort of neutron stars, just some really magnetized stars that are rotating really fast. So you'll see, the blue stuff is meant to represent strong magnetic fields, and then because they're, rapidly rotating, they're going to also produce a jet of gamma rays through its magnetic poles. And the pink stuff is that really high energy gamma rays. So these are just astrophysical objects that can create a very similar spectrum to what we see. And here you're seeing an animation of a millisecond pulsar that's sort of taking up matter from this external blob and spinning even faster. So as you eat up this matter, you can, go to really, really fast rotational speeds. And that's what we call a millisecond, because it's completing a rotation within a millisecond. And those guys can also create just a whole bunch of gamma rays. And that could also be what we're seeing. We just don't know which it is. People have written many, many papers, very, very detailed calculations about whether it's one or the other or something else. But it's still up in the air, and we're trying to sort of do more research to figure out, and it's really cool. I think there's future telescopes coming in that could give us more information, more data, so we can figure this out. But possible to exist that it could be dark matter, but it could also just be other cool stuff happening around us. Finally, for indirect detection, you can also take advantage of axion conversion. So I told you earlier that axions can convert into photons, and the signal that you see for an axion versus a photon is slightly different. So the spectrum you would see normally is just really smooth. But in the presence of a really strong magnetic field, if your axion actually converts to a photon, then the spectrum is going to be a bit more jagged. And that's another way that people are looking for dark matter, where they look at astrophysical objects, especially like galaxies with strong magnetic fields. And from the data that you get there, you can look at the spectrum and try to see what spectrum it follows. If it's smooth, or if it has some more, special information contained within that we can connect back to dark matter. But this field of research is very astrophysicsy and data heavy. And then finally, to end, we have collider production, where you kind of just create it in a collider. So I like the Large Hadron Collider. where you just have two beams of really energetic protons coming together and they collide and they just create a bunch of stuff. And stuff that, is normal matter, like visible matter, we can see. We can see visible matter. But dark matter we cannot see, which means if it were produced in a collider like this, you wouldn't see it, but it would still carry some energy with it, right? As long as you create an object, you give it some energy. And here the idea is you have some initial energy that you're putting into this detector. And after this collision has occurred, you can also measure how much energy you have. And if there is some missing energy that cannot be explained with the visible stuff that has been produced, then you know there was dark matter that we cannot see, but took away that energy. Okay, I think that's all I have for today. To conclude, it exists, makes a majority of the matter content. We haven't found it. We are, I promise, trying really hard. Thanks for listening.